Imagine a book where you have to read pages one after another, never skipping. In a disk file that is stored sequentially, the read-write head moves along the tracks just like turning pages. The total time to read n blocks is built from 3 parts. T total equals T seek initial plus n-1 times T seek plus n-1 times T rot plus n times T transfer. T seek initial time to move the head from its current place to the start of the file, like opening the book to the first page. T seek extra tiny jumps between consecutive blocks, usually almost 0 because the head stays on the same track. T rot waiting for the right sector to spin under the head. Each block needs 1 rotation, so n-1 rotations. T transfer actual data read/write time per block. For example, 0.1 milliseconds for a 4 kilobyte block. If the disk needs 8 milliseconds to seek, 4 milliseconds for 1 rotation, and transfers 0.1 milliseconds per block, reading 100 blocks costs. T total equals 8 plus 99 times 0, plus 99 times 4 plus 100 times 0.1 equals 8, plus 396 plus 10 equals 414 milliseconds. Explanation: direct random access with block address calculation. Think of a library where every book has a unique shelf and slot number. If you know the exact number, you go straight there, no need to walk through other books. In a disk, each block has a logical block number, LBN. The physical address is computed as physical address equals LBN times block size plus offset. If block size equals 4 kilobytes, and you want byte 12,345 of block 7, first find the block start. 7 times 4096 equals 28,672 bytes. Then add the offset 12,345 modulo 4,996 equals 4,153. So the byte lives at physical byte 28,672 plus 4,153 equals 32,825. The disk controller moves the head once seek and waits the right rotation latency, then reads the data, much faster than walking through all earlier blocks. Imagine a giant phone book that is too big for one page. The first page lists letters A, B, C and tells you where the page for each letter begins. That first page is an index block. If the phone book grows even more, each letter's page may itself contain another mini-index pointing to deeper pages. This is exactly how an indexed file works. Single-level index. One index block holds pointers to all data blocks. The file size it can address is number of pointers times block size. Multi-level index. An index block points to second-level index blocks, which then point to data blocks. The addressable space grows exponentially, number of pointers to the power of levels times block size. For example, with 128 pointers per block and 4 kilobyte blocks. One level can address 128 times 4 kilobytes, approximately 512 kilobytes. 2 levels can address 128 squared times 4 kilobytes, approximately 64 megabytes. 3 levels reach approximately 8 gigabytes. The operating system first reads the top-level index 1 IO, then follows the chain until it finds the exact data block. Still far fewer reads than scanning sequentially. Picture a set of mailboxes, each labeled with a number from a hash function, like the last 2 digits of a zip code. When you receive a letter, you compute its hash and drop it in the matching box. If 2 letters get the same box, a collision, you need a rule to store both. 2 common methods. Chaining. Each mailbox contains a linked list of all records that hash there. The disk block for the bucket stores a pointer to the first record. Each record points to the next. Open addressing. Linear probing. If a bucket is full, you move to the next bucket, wrap around, until you find an empty slot. In a file system, the hash function maps a file's name, or its inode number, to a bucket block. Retrieval is fast. Compute hash, go directly to the bucket, scan a short list. The downside is that when many files hash to the same bucket, the list grows and lookup time degrades, just like a crowded mailbox. Directory structures, single-level, two-level, and hierarchical models. Single-level, think of a single flat list of all your toys on a shelf, each with a unique tag. Every file lives in the same folder. Searching means scanning the whole list. 2-level, now you have a big box for each family, for example documents and pictures. The top level holds the names of these boxes, and each box contains its own list of files. You first pick the right box, then look inside, smaller searches. Hierarchical tree, this is like a family tree of folders and subfolders. The root is the house, branches are rooms, sub-branches are drawers. To find a file, you follow a path from the root down the branches. This mirrors how modern operating systems organize files, allowing unlimited nesting and logical grouping. Advantages grow from single to hierarchical. Less memory for directory entries, faster lookup, because you only scan the relevant subdirectory, and easier human navigation. Explanation, pathname resolution, and symbolic link mechanics. A pathname is like giving directions: go to the kitchen, then the left drawer, then the blue jar. The operating system starts at the root directory / reads each component and moves to the next directory until it reaches the final file. A symbolic link symlink is a shortcut or a sign that says the blue jar is actually in the pantry. When the resolver meets a symlink, it replaces the current component with the link's target path and continues resolving. Symlinks can be absolute /pantry /blue_ jar or relative .. /pantry /blue_ jar. If a symlink points to another symlink, the operating system follows the chain until it reaches a real file or hits a preset limit to avoid infinite loops. This mechanism lets you keep one copy of a file, but appear in many places, much like having one master key that works on several doors. Think of an FCB as the information card attached to every file in a library. The card does not contain the story itself, just facts about it. File name, human readables. File size, how many pages. Timestamps when added, modified, accessed. Owner and permissions, who can read or write. Location pointers, where on the disk the data blocks live, could be a single start block, a list, or an index block number. File type, regular file, directory, device. When a program opens a file, the OS loads its FCB into memory, often called in a node in Unix. The program then works with the file using the FCB's pointers. The actual data is read or written later. Keeping metadata separate from data lets the OS manage security, quotas, and quick lookups without scanning file contents. File allocation strategies: contiguous, linked, and indexed allocation. Contiguous, like storing a movie on a single DVD, all its blocks sit side by side. Easy to find just one start address and fast to read sequentially, but gaps left by deleted files cause fragmentation, making it hard to fit large new movies. Linked, imagine a treasure map where each clue points to the next location. Each block contains a pointer to the next block. The file can occupy any free blocks on the disk, so no external fragmentation. However, to reach block K you must follow K pointers, which is slower for random access. Indexed, picture a table of contents at the front of a book that lists page numbers for each chapter. The index block holds pointers to all data blocks or to other index blocks for large files. This gives direct random access like contiguous, but without needing the blocks to be physically together. The trade-off is the extra space for the index and the need to read the index block first. When a disk reads a block, 3 delays add up. Seek time, TS, moving the read-write head to the correct track, often modeled as TS equals TAVG plus K times absolute track target minus track current. For simplicity, many specifications give an average, for example, 8 milliseconds. Rotational latency, TR, waiting for the desired sector to rotate under the head. On a 7,200 RPM disk, one full rotation equals 60 seconds divided by 7,200 equals 8.33 milliseconds. So average latency equals 1/2 times 8.33, approximately 4.17 milliseconds. Transfer time, TT, time to actually stream the data, TT equals block size divided by transfer rate. With a 200 megabytes per second interface and a 4 kilobyte block, TT equals 4 kilobytes divided by 200 megabytes per second equals 0.00002 seconds equals 0.02 milliseconds. Total time for one random read. T-read equals TS plus TR plus TT, approximately 8 milliseconds, plus 4.17 milliseconds, plus 0.02 milliseconds, approximately 12.19 milliseconds. If you need to read 10 different blocks scattered across the disk, each incurs the full cost. giving roughly 10 times 12.19 milliseconds, approximately 122 milliseconds. A sequential read of those same 10 blocks would only pay the seek and latency once, then add 10 times transfer, saving many milliseconds. This math shows why file layout, contiguous versus scattered, matters for performance.